Okay guys, let's take a look at some of the stuff with your homework. As I said earlier, question number 1 in your homework is exactly the same as for you to do too. Exactly the same. We already did the point tester equation that we wrote, and we also drew in what the graph looks like. So I'll refer you to your notes for that, but let's jump into number 2. Now for any of the ones like numbers 2, 3, any of those, a lot of them say write a point tester as like the last thing. You're totally welcome to write a point tester first and then use that to check these points like up here in A and B, but you could also just directly figure out if they're fitting the description. So for example, all points that are the same distance from 4, 0 as they are from the y-axis. And again, you don't have to graph this, but I find it really helpful to look at it like a visual. So the y-axis is here, 4, 0 is here. So you're basically, if you're given a point, you're trying to determine if its distance from 4, 0 is the same as its distance to the y-axis, right? And that can be determined in many ways. So you could certainly just figure out that distance. The good thing from the y-axis is you can just count over whatever the x-coordinate is, right, and see what that distance is. But we're going to have to use the distance formula between 4, 0 and whatever point is given. On the other hand, it probably is easier instead to just jump straight into writing a point tester equation using distances and things like that. Now number 2 is actually very similar to example 2, okay, so you could refer to example 2 for this one. But you'll notice instead of a horizontal line we're looking at being equidistant to, it's actually going to be a vertical line. In this case it is the y-axis itself, but that's also the line x equals 0, right? And the distance between anything and x equals 0 is simply the absolute value of x minus 0, which is just x, right? And if some random point here, let's call it x, y, I suppose, its distance from 4, 0, right, is going to be the square root of, well, x minus 4 squared, right, plus y minus 0 squared. So I'll just leave that as y squared. Okay, and at this point you just want this distance here to be equal to that distance there, and you can then simplify that and expand it, and you should have a nice equation that comes out of that, kind of like in example 2. So again, that's a similar idea as example 2. But I'll let you kind of go through and actually answer that question for yourself. Just make sure you're understanding what it's saying. All points equidistant from this line and this given point here, and you're going to see something, a shape form again that's familiar to you as you do that one. Looking at number 3, so we have learned that a set of points equidistant from 2 given points is a line. So that's like the example 1 actually that we did, so I'll write that in here. This is in the book. This is just like example 1 in the book, number 3. But instead of saying equidistant, so if I just had these 2 points, these are the ones given, 6, 0 and 15, 0. Instead of being equidistant between the two, which would be smack in between, right? We're looking for all the points that are twice as far away from, well, let me remind myself. Twice as far away from 15, 0 as they are from 6, 0. Now interestingly, if you actually were to just look directly in between here, you can see that it's kind of split into thirds. And if I want to be twice as far away from 15, 0 as I am to 6, 0, I can find one point fairly easily that is just by looking at the x-axis here, and that would be 7, 8, 9, 0. So 9, 0 happens to be twice as far away from here as it is from there. But that's like one single point to find. How could I determine if other points are? This is again where you'd really want to utilize the idea of distance formula. Now, this is interesting, okay? So if we just had some other general point that was, let's just say, I don't know, let's just say here, let's say this is twice as far from there as it is from there, and let's just call this point x, y, right? So if this was like d, let's say, whatever the distance is, then we want this to be 2d. Does that make sense to you guys? Okay, but we can actually come up with an expression, you know, for that. Does that make sense? And what we could do is actually come up with the exact distance formula expression for this one and for this one, and then just say that it needs to be twice as long. So if I have, what's the distance from xy to 6, 0? It's the square root of blah, blah, blah. But we want that to be, in fact, actually, hold on. We want this one to be twice as much as this one, right? So actually, I should say 2 times this one equals that one, shouldn't I? Okay, so this is again kind of learning how to set these up appropriately. But whatever this distance is here, that's going to be distance formula, right? Again, from this general point xy to 6, 0. Twice that is going to be equal to the distance from xy to 15, 0. Okay, so we're going to use this as our distance there, and that is there. Okay, so again, we're kind of learning how to set this up and utilize the distance formula appropriately. So I'll let you kind of fill that in, and again, how to simplify this. We'd probably square both sides and then distribute things and then just make it look a little bit prettier and nicer. Let's take a look at question 4 a little bit here. Okay, so again, I'm going to leave you with 3 there. Question 4, we're kind of going on a different path here. We're doing something a little bit different. We're given information about a triangle and its vertices, which I've sketched out. And again, it doesn't say to, but you know, I find it really helpful. I like visual things like this. And it asks us to find equations for perpendicular bisectors. So this is also something just to kind of, you know, remember, I suppose. Remember, a perpendicular bisector by definition means it goes through that. It goes through the halfway point, aka the midpoint. So we know how to find the midpoint between 2 points, right? You can also think of it as the average point. And it says to find that for AB, and it also says to find it for AC. And the nice thing is, it looks like the way that they've made it for us, you can see the slope is 2/3 here, and that's another 2/3. So it looks like it's a nice coordinate for the midpoint. Okay, and so we're also trying to find that equation. So we've got both those equations that's asked of us in the intersection of the two. Well, if you find the equations like y equals whatever, then of course if you want to find their intersection, you can just substitute them together to find where they cross, right? So we're really, if you read the whole thing before doing any of it, A, B, and C kind of as a whole, you can see that we're trying to find where these things meet each other, essentially, there. Now, as you remember, this guy, I suppose, if you look at his slope, is going to be negative down 1/2, right? So -1/2. This guy right here, his slope, as we said already, is positive 2/3, up 2/3. So that means we can be pretty sure we know what the slope is going to have to be of these lines, right? And in fact, I might not have drawn these lines very well, but if you figure out what the slope's going to be here, so in this case, opposite reciprocal, right? So that would be -3/2 for that one. And if this is already -1/2, what's the slope of this going to have to be? I think it's going to be 2/1, or just 2. Now the good thing is, like I said, I didn't draw that very accurately, so this one actually should go up to here. And this one, if it's -3/2, it needs to go kind of down to there. So a little bit inaccurate there. But if you were to go down and trace that down, you could find the y-intercept, right? And you could write the y equals ax plus b format of the equation. Same for this one. If you know that it's going to be -3/2, then I'm going to go back 2 and up 3, and then back 2 and up 3. And then you can eventually trace it up here and see what the y-intercept is up there. And you can get your 2 equations. Alternately, it may be easier just to use the midpoint right here, right? And use its coordinates to write the formula in point slope form. And then you can just solve it for y, and that's actually maybe easier for these two. Okay, so my page looks a little messy here, but you can kind of get the idea here that the perpendicular bisectors, you can figure out the slope of this line, and then its opposite reciprocal will give you the new slope. And then you can just maybe use this midpoint here, right, to set up the point slope equation, and you could do alternately the same thing for the other one there. Okay, so there's only one more thing I was going to mention. There's a few other problems on here, but I want to kind of leave those for you to tackle yourself a bit. I want to jump over to question 11 real quick, because this is a very interesting one, and we haven't spent that much time on the idea of three-dimensional coordinates, which this has a lot of ties to that. So if we look over at example 11, now you may not realize this, but maybe you already do. I guess let me move my camera up here for you. The fact that it says z squared equals x squared plus y squared, we now have three variables involved, which tells me that, well, this is what it says: find several points that are on the graph of this equation. And that just means come up with numbers that make this work. You may come up with some easy ones, I guess, like 0, 0, and 0, or even 1, 1, and 1. And you can certainly use those, but see if you can find a few others that work. You probably realize, or maybe you remember, that this has to do with, might have to do with Pythagorean triples. If you're looking for whole numbers, you learned in geometry that any three whole numbers that fit this kind of relationship, although we used to think of it like, or usually like c squared equals a squared plus b squared, but it's still the same concept here. But also if there's decimals or something like that, that also could work. The interesting thing here is it goes through and asks us various different examples here, just specific z values. So if I have x squared plus y squared equals, let's just say z equals 5 squared, I want you to remember that x squared plus y squared equals 25 is a circle with the center at 0, 0, and the radius is 5, right? Here's the cool thing. You can actually take a look and think of this in 3D coordinates. If I were to specifically say if z equals, this was the case where z equals 5, okay? So this whole thing was when z equals 5. So if I were to actually count up when z equals 5, let's say, and let's just go by a little bit smaller of a units here. So 1, 2, 3, 4, 5. So right here at z equals 5, and this is a little bit hard to get your mind wrapped around, no pun intended. Then what we have is, I'm going to go out 5 on these axes as well, because what we have is actually, and this is kind of a weird thing, a weird funky thing to draw, but what we have is up here a circle with radius 5. Okay, but it's up here. And it's hard to draw this perfectly, but essentially we have a circle out here with radius 5 in 3 dimensions, and it's essentially horizontal here, parallel to the xy coordinate plane. And you could say the same thing about z equals 11 or even negative 11. Negative 11 is weird, but it still works, because when I square that, it's going to become positive 121, and it's still a circle of radius 11. So if I were to allow myself to go all the way down here to 11, then I'd have an even bigger circle of radius 11 here. And even if I went all the way up to positive 11 here, that would also be a circle of radius 11. You might be realizing it here, but what we're doing essentially is just stacking up. I'm not doing a good job drawing it, but we're stacking up a bunch of circles that are getting wider and wider as you go. And I'm giving this away a little bit, but I'm also kind of getting at something that it's referring to, but not implicitly or explicitly like giving away to you per se. But what this is forming actually is going to be a conical shape. You can actually get a 3D graphing app, the GeoGebra 3D grapher. I'll write that here. And you can actually type, the equation z squared equals x squared plus y squared, and it will actually graph it, and you'll see that it's forming a cone like that. So you can kind of go through that one yourself too, but I just thought I'd have take a little bit of time to kind of chat about these problems, these few specific ones that I selected here to have you work on. So that's it for the rest of this thing, and I will talk to you guys later.